Hey, how you guys doing? So I figured we should, I guess, get started. Man, we're almost done with this chapter here. So at the end, I want to bring up the calendar and be nice and clear where we're headed in these last 2 weeks. Okay, but right now, my job is to finish this chapter, which we're not going to do. We'll probably finish it Monday, but we need to talk about this stuff. So let's go do this. So I'm going to go share my OneNote. We were at the end of this one problem. We were looking at the natural response of this guy. So we derived the differential equation. And when we derived the differential equation, we ended up with s squared plus 4s plus 2 for VC. And then we checked it because we could see here that when the switch opened, there is no source. And since capacitors and inductors are passive elements, we don't have to, we know that the effective source on this guy has to be 0. No doubt about it. So now what we got to go do here is that we got to go get the natural response of this thing. So again, this tells us that the forcing constant, right? This forcing constant is 0. That's all I know. So here I go. So now what I'm going to do here is that I'm going to look at that equation. So my characteristic equation is this guy. So it's s squared plus 4s plus 2 equals to 0. So one thing that I always try to do here is that, so when I'm comparing this, I either compare these two or I try to eye it. And the easiest thing to do here is that when you go and try to eye this thing, you could see here that, wait, did I get this right? Let me see here. I have an error. I'm thinking I have an error, and look at why I have an error. This is 4 and I have 2. So obviously I have some number error that I'm screwing up with. That's 1/2. I don't see my number error here. I don't see a number error. I mean, if there is, it's not obvious to me right away. Let's see, if this is a quarter, well, if there's a number error, I'm going to not try to do that. I'm not going to focus on that. So for right now, I'm just going to keep moving along. So this tells me here that 2 alpha must equal to 4 and omega squared has to be equal to 2. So then I'm seeing here that alpha is 2 and that has to be greater than omega naught, right? And then omega naught here has to be the square root of 2. So then this tells me that it's overdamped. So then it immediately tells me that I have to go, my solution then isn't going to look like this here. I'm going to see that VC of t is going to be some natural response times some force response, but we already saw that this force response was 0. And if this force response, then I'm going to get a solution that looks something like this. That looks like that. And so therefore, that's what it's going to be. So, you know what? I got to go close this door because somebody is using an air blower and I got to stop this noise. Give me a second. Okay, sorry about that. So now let's keep going along. So now let's go look at the process. So if I look at my process, what am I seeing? That here's our problem-solving strategies. So if I look at this thing here, it looks like this. So we've now have learned how to derive the second order equation. We've now have gotten the general response. So now our job is to get the initial conditions and then determine the constants A1 and A2. You're going to see that this is really a one-step process, but I'm going to separate them just to be, as clear as possible here. Okay, so now let's go do this. So this can be a really tricky step here. Why can it be a tricky step? The algebra can get really intense. So here we go. We're on step 3. Here we need to determine the initial conditions. And there's 2 of them. In the end, we have to get 2 of them. It's got to be 0 plus and the derivative of 0 plus. And you're going to see that it's the derivative one that's the real problem. So here we go. What we find here is that up to this point, we have a general response. And that general response looks like this here. Of course, there's a natural, and then there's a forced response. And then our natural gives us 2 constants. And then we know our forced response from step 1. So now what we have to do here is that we have to apply initial conditions to get A1 and A2. Next, we must determine A1 and A2, which are the integration constants, A1 and A2, by applying the initial conditions at t equal to 0. And I should be really careful. It should be 0 plus. And so what you're going to find here is that there can be 4 unknowns. That means you're going to have, it's mandatory that you get these 2. But you're going to find that in certain circuits, I might have to solve a 2 by 2 to get one of these. So the minimum requirement is that you need a minimum of 3, but you may have more unknowns. And so the process of the strategies here are pretty straightforward. And they follow along the same lines as our previous strategies that we did with the first order circuits. So we got to determine the numerical values of VC and IL at 0 plus. But of course, we do this at 0 minus. Next, we need to determine the numerical value for the derivative of the variable that we're trying to solve for. So here's where it's really nice if you've defined step 2. You defined, variable 1 and variable 2. And what you're going to see here is that I'm going to try not to get you to think in terms of variable 1 and variable 2, that what you're doing here is that you're solving 2 equations and 2 unknowns. That's really what we got to get. Okay, that's what we want to do. But if you get stuck, you go back to step one. And in step one, you have two first order equations. And your job here is to find the derivative of the variable that you're trying to solve for. So the way we'll do this here is that we want to go in and we want to look at an example, of course. So let me go get this example. And I'm going to apply this. Let me see if that's, do I want to jump into an example? Yeah, I think I'm just going to jump into an example. So here's the example. Okay, here's 8.4. So I want to do this example just to get you moving here. So again, what am I going to do? We're going to derive the differential equation, of course. We got to keep practicing you as much as possible. So let's go do this. So what I'm going to do here is that I'm going to derive the second order equation. Right? That's step one. So here I go. So when I'm looking at this guy, what am I seeing here? Well, I could see that I have the cap. Look at the current. So we can clearly see that the current's got to be going in this direction for the inductor. And we can clearly see that this guy has to have the cap voltage like this. There are some second order differential equations where it's super, super hard to actually look and see which direction the current is going to be going. So here we go. So when we're looking at this, of course, we look at 0 plus here. So that means I have a 2 ohm resistor in there. So let's go do that. So here I go. So I'm going to look at KCL. And if I do that, I can clearly see that if I look at this node right here, that node tells me that I have 5 half amps coming in, and it splits. So I'm then going to write here, the first thing I'm going to write here is I'm going to get IC plus IL, and I'm going to write 5 half amps later on. But then look at this guy here. IC is the guy I got to convert, right? I got to convert this guy. So if I convert that guy, I have an eighth. So this should be 1/8 S hat VC IL, no resistors. So therefore, this is 5 halves. So I got my first equation right here. Okay, got my first equation. Now let's go apply KVL. So when I look at KVL, you can see I got to go through the outside, right? Here's my KVL loop. I got to go all the way around. So if I go and I do that, we're going to see that KVL tells me that I got this guy. So if I look at the polarity, what I'm going to do here is that I immediately see here that I'm going to start with the inductor. So with the inductor, what I'm seeing here is that I have what? I have plus or minus VL like this. So here I go. So I look at VC, that's going to be positive. This guy, the 6 ohm, what you're going to see here is that that 6 ohm tells me that I have IC here. And this guy has, of course, IL going through it. So now I can write my voltage equations here. So my left side tells me that I have VC. Then I got the voltage across the 6 ohm resistor, which will be 6 IC. Now I got the left side. Now remember, these guys are negative. So in this case here, I'm going to get minus 2 IL minus VL. And that's going to be equal to 0. So now I got to convert IC and I got to convert VL. Let's go do that. So if I convert IC, note that that's an eighth. So I'm going to get VC plus 6/8 S hat VC. Then I get minus 2IL. I got to convert L. Look at that, I got 2, so then this should be 2 S hat IL equals to 0. So now I got my second equation. So if I look at this thing, I could then go in and matrix this guy. So let's collect the VC terms. So I got my VC terms is going to look like what? I'm going to get 1/8 S hat VC. I look at the left, so I'm going to get 1 plus 6/8. So I'm going to reduce that. So that should be 3/4. And then I look at my IL. My term here should be minus 2. What should it should? It should be minus 2, 1 plus S hat. And then I should get 1. There's my operator matrix. And then I get 5/2 and 0. So here I go. So what I got to get now is I got to do what? I got to come in here. Let me think here. I want to see if I can get this cleanly here. So if I look at my matrix here, I'm going to look at that D here. So then I'm going to get, this tells me that I got my D operator and I'm solving for the inductor voltage, right? The inductor voltage. And now look at this. So I got to take my constants and I got to put it with my ILs. So this should be this guy. Oh, I put a VC in here. That shouldn't be there. I have 1 plus 3/4 S hat. Then I get 5/2 and 0. And so if I do my matrix, you could see that the term is 0. And then I'm going to get S hat operated on 5/2. So I should get minus 5/2. Okay, so I now know what my constant is. So now I got to go, I'm going to go after my D operator. So let's go do that. So my D operator of acting on IL is then going to be this guy right here, right? That's how I'm going to get my D operator. So now if I do the algebra, I'm going to get minus, I have 2/8 S hat operating on 1 plus S hat minus this guy, which would be minus 1 minus 3/4 S hat, and that's D. Now let's see if I can clean this up. So the first thing that I see here is that look at my minus signs. I got a minus sign here, minus sign here, minus sign here, and a minus sign there. So I'm going to get rid of all the minus signs. So there's no minus signs. So now I'm going to focus on just trying to not make any mistakes. Okay. So I got S squared. So I'm going to get 1/4 S squared hat. Then I'm going to get 1/4 S hat. I get plus 1. And then I'm going to get plus 3/4 S hat plus 1. So then this guy has to equal 5/2. So look what I'm going to do. I'm going to multiply through this guy with a 4 here. So if I multiply this thing by 4, then I'm going to get it has squared S hat plus 3. Oh, wait a minute. This is 4 over that, so I should get 4 S hat. And then I'm going to get 4 right here. Okay, don't let me make mistakes. That looks clean to me. And then I got to multiply 4 times 5, which is 20. 20 divided by 2 gives me 10. So here is my second order equation. Okay, here is my second order equation. So if I look at this guy, Now, what am I going to do here? I'm going to go to step 2. I want to determine the natural response. So if I look at the natural response, oh, dude, we got to check this. We got to check the circuit. Let's do the check. So if IL at infinity is a constant, if I plug this guy in here, what is this thing? I get 0 plus 0 plus 4b equals 10. That tells me then that b has to be 5/2. Does that match up with the circuit? This guy goes to a short, that guy goes to an open. So you could see here is that at I equal to infinity, I'm going to get a circuit that looks like this. I get an open. I get 5/2, and then I have a 2 ohm. But I know that the current of the 2 ohm has to be the current of the inductor, and of course, that's 5/2 amps. Okay, so that checks out for us. So I now know what B is. Let's go get the natural response now. If I get the natural response, I'm going to focus on the, so I have my characteristic equation and roots. So here we go. So I can click that one. I think that's an easy one, right? That's 2 and 2. So I look at this equation and I could immediately write this as S like this. So this immediately tells me that S1 and S2 both must be -2. The only way this could be true here is that if I have what? Critical damping. Right? It's critical damping. So here I go. I now know I have critical damping. That means I don't have a choice with the solution. I have my natural response and I have my forced response. So then my critical damping means that it's got to be e to the minus 2t times a1t, a2, look at my two constants, plus b. But b in this case we saw was 5/2. Here I go. So now I have my general response. So now I got to go to step 3. Step 3 then says go determine the initial conditions. Okay, go determine the initial conditions. So let's go look at what the strategy says. Right? The strategies say what? They say determine VC and IL as normal. So let's go do that. So at t equal to 0 minus, what does my circuit look like? Look at my circuit here. Let me see if I can go get that circuit. Here's my circuit. So if I look at the circuit at t equal to 0 minus, you can see here that I have what? I have this guy. I have an open. I have a source. I have a shorted inductor, which means that it looks like this here. So when I look at this guy, you can see here that my inductor tells me what? It tells me that VC immediately, you know what, I should have done this like this. So this is IL and this is VC. You can see that the inductor kills off the capacitor voltage. So this immediately tells me that VC of 0 minus, which is of course VC of 0 plus, is 0. IL of 0 plus is then going to be 5/2 amps. Okay, I got my 2 of them. Now what I got to do here is that I now go to step 1.
Wait, hey, Carlos.
Yeah.
Would the VC still have a voltage because of that 2 ohm resistor?
No, it's an open. It's a dead resistor.
One that's in series with the inductor?
Oh no, look at that. At t equal to 0 minus, that guy's shorted out.
Oh, sorry.
Yeah, no problem. Go to step 1 and look at both Kirchhoff's equations. So if I come all the way up to step 1, where are they at? Here they are, right? It's these guys. These are Kirchhoff's equations right here. So if I come and I bring them back down, these are from step 1, you could see here is that I have this guy and I have this guy right here. And so here's what I'm trying to get you to think in terms of the language of what? Right, so this guy right here is KCL, right? Here's KCL. And this guy's KVL. And the question is, what are we solving for? We're solving for the inductor current. So if I'm solving for the inductor current, the variable that I need is S hat squared. Since we are solving for IL of t, we need S hat IL of t at 0 plus. So these are the equations. And look at this guy. You could come in here and you could just say, well, look, here it is. But there's a problem. It depends on S hat VC. So what I have to do here is I essentially have to also pay attention to S hat VC in KCL. So I need both of these guys here. And this is very common in real differential equations. So now we must, what we have to do here is that we have to solve for that, that condition right there. So here we go. So what you're going to see here is that we must solve for S hat VC as well. So here I go. So now what I'm going to do here is that looking at the KVL equation, we solve for S hat IL of 0 plus. So if you do that, look what I'm going to get. I'm going to get what? I got S hat IL of 0 plus. And then I'm going to take it to the other side. Note that it has a 2 here. So there's my 1/2 right there. And then I'm going to get the expression what? VC of 0 plus, what is that? 2/3, right? Yeah. 2/4, sorry, 3/4 of S hat VC of 0 plus minus 2 IL of 0 plus. And you could see how right now I need 3 of them. The minimum that I need is 3 of them. We've already solved for 2 of them. So now I got to go get that. So then what I'm going to do here is that I'm going to do the following thing. I'm going to use the KCL equation to get S hat VC of 0 plus. And you could see here, so if I do that, we then have the following thing here. So from a KCL equation, you could see here that I'm going to get S hat VC. Now note, there's my eighth, and then this should be 5 halves minus IL of 0 plus. So I'm going to compute that. So if I compute that, what you're seeing here is that according to what we already calculated, look what we have. IL of 0 plus is 5 halves. So that means I know that IL of 0 plus is equal to 5 halves. So when I substitute this in, you could see that I'm going to get 0 for S hat VC of 0 plus.
Carlos, what is it? 1/8? I don't see why.
I can't hear you.
In KCL, why is it solving for SBC 1/8? Why?
Because when you look at that equation, we have an 8 right here. Oh, so it's multiplied by 8.
Multiplied
Sorry.
by 8, right? Okay.
Yeah, thank you. Multiplied by 8. Thank you for the correction. And so it's 0. So now I could then go in and we could see that this term here gets canceled out. So then if I look at this guy, here's what I have. I have that. So back to S hat IL of 0 plus, we see that S hat IL of 0 plus, we see that it's 1/2. This guy, VC of 0 plus, we already saw was 0. So then I'm going to come in, I'm going to put 0. Then I get 3/4 times 0. And then I get minus 2 times 5 halves. So then what I'm seeing here is that the answer that I'm going to get then is going to be minus 5 halves for, is that right? Am I getting minus? Let me make sure here. Looks like that's what I'm getting for my current here. Assuming that I don't have any mistakes here, my algebra looks good to me. Okay, so then that's my initial condition right there. So now I have my initial condition that I need to then go in and solve for A1 and A2. Okay, let's go to the next step here. So remember, I said step 3 and step 4 are really one and the same. Okay, so let's go look at this guy. So last step, step 4, we want to determine constants A1 and A2 and write out the complete response. And this is where we're really, this is the end of the thing. Anything else is just in solving the problem here. Here's where it gets messy. So now what we've done here is that with step 3, we now have the 2 initial conditions, right? X of 0 plus and S hat X of 0 plus. So now we got to apply them. So we must apply these to the general response. Equation to determine A1 and A2. And so the algebra gets tricky here, right? This is messy. It's messier right now than what it actually is, but let's look at critical damping. So if I look at critical damping, we know what the solution is. We know that x of t critical is then going to be e to the minus alpha t, a1t plus a2. So then if I apply the boundary conditions or the initial conditions, to solution, and I'm pretty sure this is the exact same thing that you did in math 7 here. Then here I go. So then I'm going to just say, okay, for critical at 0 plus, I look at the solution here, and you could see here that I'm going to get what? Oh, by the way, there's also my constant b. I can't forget about my constant b. Whew, that was close. So then that means here, this guy is then going to be e to the 0 times a times 0 plus a2 plus b. So then, of course, this has to be a2 plus b. And then if I take the derivative of this guy for 0 plus, then I got to take the derivative of this guy. So if I take the derivative of this guy, of course, I'm talking about this guy of e to the minus alpha t, a1t plus a2 plus b. So you can see here that the b constant is 0. So I ignore that. So if I take the derivative of this guy, I got to use the chain rule. So it's got to be minus alpha e to the 0 now times a1 times 0 plus a2. And then according to the chain rule, then I get e to the 0. So now I focus on the inside term. And the inside term says I take the derivative of that, I'm going to get a1 plus 0. So when I look at this algebra here, it looks like my algebra says it should be minus alpha a1, no, a2 plus a1. So that's how I'm going to get it. So now what you see here is that I have two equations, two unknowns. So when I look at this thing, this guy's going to be x critical. At 0 plus is going to be a2 plus b2. And then s hat x critical is then going to give me minus alpha a2 plus a1. Two equations, two unknowns. Right? No surprise. That's what they're going to do right there. So I'm going to try to be a little bit more faster now. So if I look at overdamped, we know that overdamp is then going to be a1 e to the s1t plus a2 e to the s2t. So now I just do the exact same thing. Again, I keep forgetting my damn constant b. So if I just write this out quickly, we could see that over at 0 plus is going to give me this, since the exponentials give you 1. If I take the derivative of this thing, then there's nothing fancy about this, right? I just get S1 and S2, then the exponentials give me 1, so I'm going to get S1, A1, S2, A2, and here's my two equations right here. And then the same thing happens with underdamped. Underdamped, of course, has more algebra, because of the cosines and the sines. So in this case here, I'm going to have, so for under, I'm going to get e to the minus alpha t, a1 cosine omega d t plus a2 sine omega d t plus b. So now I just got to take the derivatives of, in this case, not the derivative yet, but x under of 0 plus. The sine is 0, so I shouldn't have a constant a2, so then I should have a1 cosine of 0, which is 1, and then I have my constant b. So now let's go look at the derivative of this guy. If I look at the derivative of this guy, I got to use the chain rule. So this is very similar to the one with that's critical, right? The chain rule is going to give me minus alpha a2. But in this case, it's not a2 because it's the cosine that's going to survive. And I'm sorry, it's going to be a1 because, right, it's got to be because the sine is going to turn, here, let me be careful. I'm going to have to just do it. So if I take the derivative using the chain rule of the exponential, I should get minus alpha. And then I'm going to set e to the 0, which is 1. And then if I set 0, yep, it's a1. And then a2 term is going to be 0. Okay. Then the second term, now I take the derivative of the inside. So if I take the derivative of cosine, I'm going to get a sine. So when I set sine equal to 0, that's not going to work. So then it's the sine term that's going to give me that. So then I'm going to get the derivative of sine is cosine, but then I'm going to get an omega d, and then I'm going to get cosine of 0, which is 1. So then these are my two things here. So now we're set here. I have my boundary conditions. And so now I'm going to go solve for my boundary conditions here. Okay. So I have two problems that I got to do. So let's go do those two problems completely.
Carlos, are we going to finish the first one or no?
Oh, I forgot about that one. So let's go look at this guy again. So what we have here. So what is that example? Is that example?
It was 8.4.
8.4. Okay. So if I look at this example here, assuming that my stuff is right here. So I know that my solution to this thing, we wrote down, where did we write it down? We knew that, we said that this guy was critically damped. So we got critical damping here. So if I come back here, let me go still this guy. So that what this tells us here is that our general response is this guy right here. So if this is our general response, so now I've got to go apply the initial conditions that we solved for. Okay, so here's my general response. So now our initial conditions for the circuit are what we did already. So I'm going to go back and get those. And they're right here. So I see that this guy has to be this guy. I'm going to bring this right here. And I'm pretty certain that IL of 0 plus was 5/2. And then S hat IL of 0 plus is minus 5/2. So now what I'm going to do here is that I'm going to apply these. So now apply these to the general response. To get A1 and A2. So if I do that, then I'm going to get that IL of 0 plus is then going to be e to the 0 times A1 times 0 plus A2 plus 5/2. So then we see that I get A2 plus 5/2. So now I got to take the derivative of this guy. So S hat IL at 0 plus tells me that I got to take the derivative of this guy. So now I got to use the chain rule. So then it's got to be minus 2 times e to the 0. Then I get A1. Oh, wait a minute. Yeah, A1 plus A2 plus e to the 0 times the derivative of the inside, which should give me A1 plus 0, and then, of course, plus 0 when I take the derivative of the constant. So if I look at my algebra, it should be minus 2A1, no, A2, plus A1, and this guy should equal, according to, so that's what that is right there. So now, here I go. So just to clean this up, what am I doing here? Well, I know that IL of 0 plus, our initial condition is that it's equal to 5/2. So this guy has to be A2 plus 5/2 like this. And then IL of 0 plus S hat, we saw that this guy was equal to minus 5/2. And this has to be equation A1 minus 2A2. So now what I have here is that you could see is that I have two equations, two unknowns. So what I'm getting here is that I have two equations, two unknowns. So what you're seeing here is that from the first equation, we immediately see that A2 is 0. So we now know what A2 is. From equation 2, if A2 is 0, we could see then that A1 must be minus 5/2. This tells us then that the complete response now is then going to look something like this here. It's going to be that I have IL of t. We know that it's e to the minus 2, right? Minus 2. A1 is then going to be minus 5/2 times t, and then A2 is 0, and then I get this 5/2 right here. So if I look at the solution here, you could see that this solution then should be 5/2 times 1 minus t e to the minus 2t. This is the complete response of the inductor. So now I've applied the initial conditions to that whole thing. So now to try to put it all together, I want to go in and I want to start looking at the process here. So I got two of them. I don't think I'm going to finish this. So let's start it, and then we should stop about 5 minutes before class ends so that we talk. Okay, here we go. Now we have a circuit problem. Look what it says. We want to determine the voltage of the 8 ohm resistor, not the capacitor, not the inductor. And what they're telling us here is that this guy turns on at t equal to 0 plus. So that means here is that at 0 minus, there's no 1 amp source. And I could see here is that look at the polarity of the capacitor. It's in the opposite direction of the current. And because it's in the opposite direction of the current, what's that telling me here is that I expect that I have to give it a minus sign. So note that the polarity of cap is opposite of current source. This implies that VC of 0 minus is really what? Minus 5 volts, not 5 volts. Because we have to pay attention to that. So now the question is, what is easier for you to solve in this problem? Is it easier to solve for the voltage of the capacitor? Or is it easier to solve for the current of the inductor? Well, the first thing that I would do here is that I want to look at, so now the question is this. Do we solve for VC of t or IL of t? What determines this, believe it or not, is that 4 ohm resistor. Because if I look at that 4 ohm resistor, there's two things that I can look at. Do I want to look at the current of the capacitor? Or do I want to look at the current of the inductor? I would say choose IL instead of IC, because IC requires you to take the derivative of the capacitor, and that's messy. So I would not do that. I would pick the inductor. So what I'm going to say then is then solve for the inductor current. So that's what we'll do then. So let's go look at that. So what I'm going to do then is that I'm going to go to step 1 now. Step 1, I need to determine second order equation. Let's go look at that. Here I go. We can see here is that if I'm looking at the currents, this current, these guys are in series, so that makes sense. So then at t equal to 0, that implies here that the 1 amp source is on. So now I have to include that. So if I look at KCL at this node right here, I'm going to focus on this node right here. You could see here that KCL tells me that I'm going to have those currents here. Oh, I'm already solving the problem. I got to stop solving the problem. So if I look at KCL, I got to relate IL and IC. So that immediately tells you that IL must equal IC. And then I'm going to convert this. So then I'm going to go IL minus, and look what I get. I get 1/20th S hat VC, and this is equal to 0. So I now have my first equation. Let's go to KVL. So I got to relate those two voltages. So it makes, there's only really one loop. Since the 8 and the 1 amp source are in parallel, there's only this loop that I can consider. So if I do that, that means then we assume polarities like this across these resistors. And this is the reason why we picked the inductor. So let's go look at that. So I have the voltage of the 4 ohm resistor plus the voltage of the cap plus the voltage of the inductor minus the voltage of the 8 ohm resistor. And of course, that's equal to 0. So let's keep moving along. So now I see that the inductor is in series with the 4 ohm. So then I'm going to write this as 4IL. I got my VC. Now look at my inductor here. My inductor here, I have a 2 Henry, so this should be plus 2 S hat IL. I got the 8 ohm resistor here. Let's look at the 8 ohm resistor. If I look at the 8 ohm resistor, we already see here is that I have 1 amp coming in here. And then I know that my current coming in this direction is IL. So then the current of the 8 ohm, excuse me, should be 1 minus IL. So then I'm going to come over here and I'm going to write this as minus 8, 1 minus IL equals to 0. Now let's clean it up. So if I clean this guy up, I'm going to take my 8 to the other side and I'm going to start to look at my VCs here. So then I'm going to rewrite this as VC. Now look what I get. I get a minus, and a minus gives me a plus 8 plus 4 is 12. So then I'm going to get 12 IL plus 2 S hat IL equals 8. I have my second equation.
Carlos, can I ask a quick question?
Of course.
In our KBO loop, we're calling BC to be positive only because we're already counting for the fact that it's going to be a negative voltage.
Well, at 0 plus, we have to agree that the current source is going to dominate the circuit.
Mm-hmm.
So the polarity of the cap, even though it may start off negative, is going to go in the positive direction.
Okay.
By the way, that's a subtle issue right there. So now here I go. I'm going to matrix this guy up. So here I go. I got minus 120 S hat for VC, 1. Now I'm going to focus on the bottom one first. So then I'm going to get 12 plus 2 S hat. And then on top, I get 1. And then I have VC, IL. And then I got to set up my constant. And my constant terms here are going to be 0 and 8. So here I go. So then I have my operator, and I'm looking at IL. So then I take my constants and I put it into the IL column. So I get minus 20 S hat, 1, and then I'm going to get 0, and then I'm going to have 8. I got to take that. And you can see here, S hat operating on 8 gives me 0. Man, that means that inductor current better go to 0. Okay, let's go look up this thing here. It is going to go to 0 because the capacitor is in series. I forgot about that. So good. That's a good sign for me. So now I got to calculate D. So here I go. This is my D hat. Let's calculate that. So then I do the cross. So I'm going to get minus 20 S hat operating on 12 plus 2 S hat. And then I do the cross, which I get -1 IL. And then look at, because this is 0, I can get rid of the minus signs, right? I can get rid of the minus signs. So if I get rid of the minus signs, then I'm going to focus on this. So this should be 220 s hat squared plus 1220 s hat plus 1 equals to 0. So now I'm going to clean this up. So you could see that this is a 10th on this guy right here. So I'm going to multiply everything by 10. So if I multiply everything by 10, then what I'm going to get here is I'm going to get s hat squared plus 10 times 12 over 20 plus 10 IL equals to 0. So if I clean this up, I'm then going to get what? 1/2. So I'm going to get plus 6 s hat plus 10 IL equals to 0. I now have my second order equation. So if I have my second order equation, let's go do the check. And we already did the check. And we see here that if I look at the IL at infinity, which I define as B, when I plug B into here, I'm going to get 0 plus 0 plus 10B equals to 0. That tells you that B is then going to be 0. And when we look at the circuit, we could see here is that as the capacitor charges, I'm going to get 0 current of the inductor. So we could say here is that this checks out with circuit. Okay, now I know it checks out with the circuit. So now I'm going to go to step 2. So in step 2, what we got to do here is we got to go determine the general response here. So let's go look at this thing. So I need to determine general response. So we can ignore the B constant since it's 0 here. So here I go. I get from my characteristic equation, I get my roots. So here I go. So I'm going to get s squared plus 6s plus 10 equals 0. So when I look at this guy, what am I seeing here? Well, I'm going to compare this guy to this guy. So immediately I can see that 2 alpha must be 6. Alpha is 3. And then I get omega naught squared equal to 10. Wow, this guy is underdamped. So this clearly tells me that omega naught is greater than alpha, so I have underdamping. Okay, so here I go. That means then the general response is then going to be IL of t, which will be e to the alpha times a1 cosine omega dt plus a2 sine omega dt. Where I really got to do this guy here. Omega d is going to be omega naught squared minus alpha squared. Oh, the numbers turn out nice. And then I'm going to get 3 squared. So that's going to be 1. So that's sweet. So now I can really write this guy here. And here we go. Here's our general response. So now I got this guy. I go to step 3. So step 3 here, I got to go calculate the initial conditions here. I need to determine the initial conditions. So at t equal to 0 minus, remember there's no current source. So what we found here is we found this here. What we ended up finding here is that our circuit looks like this here. I have a capacitor that's open. And I have no source. Nothing's there. And I know that this guy starts off like this, which is 5 volts. And then clearly I have no inductor current because there's no source. So immediately I could say then that VC of 0 minus is 5 volts and IL at 0 minus is 0. So I now have those guys right here. Now we have 0 plus. And what we got to do here is that we got to go in and we got to look at our KCL and KVL equations here. So now look at KCL or KVL to find S hat IL of 0 plus. We may need both here. So I'm going to come up here. Where are they at? They're right here. So I'm going to copy these guys and bring them down. So here they are. So what I'm seeing here is that I'm seeing this thing here. Here's my KCL equation. And then here's my KVL. And so my KVL looks like this. And we're looking for the second derivative. You can see that it's not in KCL, but it is in KVL. So therefore, what I do now is that I solve for S hat IL of 0 plus. So if I do that, then I'm going to get, I have S hat IL of 0 plus. I have a half, so I'm going to bring a half there. So then I got to bring everything over. So then I'm going to get the quantity 8 minus, let me make sure, VC of 0 plus minus 12IL of 0 plus. So what do I know? I know that VC of 0 plus is minus 5 volts. And I know that IL at 0 plus is 0 volts. So it immediately tells me that this guy is 0. And so when I look at this guy, I'm going to get that S hat IL of 0 plus is then going to be, look at my 2 here. I'm going to bring it in. So this will give me 4 minus 1/2. And then I get minus 5. So then this should give me 4 plus 2.5 should give me plus 6.5. And this will be amps per second. Assuming that I have my right algebra here. So now I have my initial condition. I have both of them. So here I go. Now what I'm going to do here is that I go to step 4 and I need to determine constants A1 and A2. So if I do that, I now have my general response solution. Right, so we know that our general response is this guy right here. So, and I'm going to apply the initial conditions to determine A1 and A2. So here I go. So I know that IL of 0 plus is then going to be what? Well, we know that that guy, we already said is 0. So we know this is 0. So then this means that I get e to the 0 times A1 times 1 plus A2 plus 0. So this immediately tells us that A1 must be 0. Okay, so that simplifies things. And then I look at S hat IL of 0 plus, and we see that it's what? 13 halves or 6.5. And this guy tells me I got to take the derivative of this. But remember, I have no A1 term anymore. So I'm really taking the derivative of this guy now. So then I'm gonna take the derivative of minus 3t times A2 sine of t. So if I do that, here I go. So if I take the derivative of this guy, it's got to be what? Minus 3. And then, of course, I get the e to the 0. But then look what I get. A2 times 0, so there's no contribution there. Then according to the chain rule, I'm going to get e to the 0 times the derivative of this guy. The derivative of sine is just cosine, so then I'm going to get A2 cosine of 0. So then that tells me that I'm going to get 0 plus A2. So therefore, this tells me here that A2 should be 13.2 or 6.5. So I now have my constants. This means here that the complete response of the inductor is then going to be IL of t. And if I look at this thing, A1 is gone here, so this should be, it should be, let me make sure I get this right. It should be what? 13 halves e to the minus 3t sine of t. And now I have my complete response. So now that we got that, guess what? There's a step 5. Solve the circuit problem. So if I go back to our question here, let me go grab it and bring it down here. It looks like this. Here, where's my mouse? Right here. So this is what the question is. I got to solve for the voltage across that. So if I look at this thing here, here's what we just calculated. We calculated the inductor current going this way. And we know that this guy is coming in this way. So I know the current through the 8 ohm resistor. So what this tells me here is that the current is then going to be I8 of ohm is going to be 1 minus IL. So therefore, the voltage is going to be 8 times 1 minus IL. So this should be 8 minus 8 times 13 and to 2 e to the minus 3t sine of t. Now, what I got to do here is that I got to go in and clean this up here. And if I multiply, what is it? 4 times 13, I believe that's 52. Where's my mouse at? Let me get my mouse someplace. So here I go. So this guy should be 8 minus 52 times e to the minus 3t sine of t. And I now know what this guy is. So now that I have this thing, my job here is to plot and interpret this guy. I think I'm going to stop here, and I'll have to pick this up on Monday.